last time we stopped at routing, we saw two cases. Let me revise all of the cases and categories. So we quickly go through this. There are two algorithms or class of algorithms. One is the distance vector and the second one is link state. So now, do you remember what is distance vector and link state? What is the big difference?
In the link state, we have the complete information of the whole system.
Yes.
While in distance vector, we have only neighbors information.
That's right. So in link state, every node gets to know the whole topology of the network, and then it can find out from A to B what is the shortest path. In distance vector, every node does not have this information. They only exchange some information from their neighbors, and neighbors will tell them about their neighbors and so on. The distance vector does not have, every node does not have the entire picture of the network. So these are the two standard routing algorithms. And in MANET there are two algorithms which are related to this, but there is a difference. It's OLSR and OD. Then we saw layer 2 and layer 3 and what is the difference between these two as far as routing is concerned. So overall we saw three classes of networks. So one was the infrastructure mode where there is only one access point and these are the mobile nodes. Access point is static, it never moves. So mobile nodes are always within one hop of the access point. So they can directly talk to the access point. Now these nodes can be mobile, it can move from here to here and back and so on. And it doesn't matter because the base station is static, you can always talk to the base station. So that is a case 0 of mobility. On top of that, what we can do is we can have multiple of these access points, and this is our cellular network. And the mobile node goes from one access point to another to third and fourth and so on. Again, there is a static network which is always there, and the node has to just talk to the static node. That is another way. The most complex or the most general case is ad hoc mode, where there is no static infrastructure, there is no backbone. Everybody is mobile and you cannot assume anything about your neighbors. So that is the complex case, and this is what we will see in the routing protocols. So before jumping to the routing protocol, we saw how we can do the simplest case, the most basic case I talked about, the infrastructure mode, using just layer 2. So what happens is if a node wants to send packet within its own subnetwork, within its own network, then you don't need a complex routing algorithm. You just need to have a translation from IP address to MAC address, and then you give this packet as a frame to the link layer 2, which is the MAC layer, and then the MAC layer will, since it can directly communicate or it will communicate via the base station, it will send the frame there. This is simple case. This is also routing because you go from one node to the base station and from base station to that another node. Right? There is routing happening, but you don't need a routing algorithm. You just need a table. Translate from one address to another address. And this ARP protocol provides you with the translation. So you can translate an IP address to the MAC address, and then you can send the packet. This is totally happening in layer 2, and the time when we need actual layer 3 routing is when two nodes are not in the same subnetwork. So they are in a different subnetwork. This is one example. See 10.0.1.3 and 10.469. These two are not in the same subnetwork. So that's why you cannot get a MAC address of this, because nobody knows here what is the MAC address of this, and even if it knows, it's pointless, right? Because the node is far off. So that's why you need the help of routers. So all the nodes, the host node will be represented as a circle, and the router, as you see, is represented as a square. Okay. So a router is any entity which has got two interfaces with different subnetworks. This is how you can define mathematically a router. A router, so this you see, it has two interfaces. It has to have minimum two interfaces, and this is a different subnetwork. This is a separate subnetwork. So this is a router, okay. And you can connect multiple of these routers whenever you connect two routers, then the interface or the link which is connecting these two interfaces will have the same subnet. Okay? So this is how you construct a big network. Right? And now this router has to know something, router has to know something, and this no. So the concept that I introduced last time, does anyone remember what is the default route that you use? If you gateway, right? So every machine has got a default route. If the address is not self, it is 127.0.0.1. If it is not self, if you are sending a packet to any IP address which is not the self IP address, then you will contact the gateway. That is the simplest routing. Right? So for this node, this will be the gateway. This router is the gateway. Okay? So it will come, the packet will come here. Okay? So there is no intelligence here, or at least not much. Now this router has to talk to this router and find out where this can send packets. So this will advertise, I can send packets to 10.4.6.x. So if this router, let's even number this, so this is R1, this is R2. If R2 tells R1 that I can send packets to this subnetwork 6.x, then when a packet for 10.4.6.9 comes here, this router knows that my neighborhood router knows how to send packet there. So it will give a packet here. The packet will come here, and then this node knows that on my second interface and directly connected to this, it will send a packet. So this is how the whole routing happens in the entire network. And we will see how R1 and R2 know about 6.x. That is the algorithm that we will execute. So this is all now algorithms. If you have taken this course, this kind of algorithms in the computer algorithm course, you will be familiar with this. We will not go into the complexity of algorithm, right? So order, O notation and all. So we will just introduce the algorithm and assume that these are the best possible. So we need to, so the router has to do two things. One is it has to forward packets, which is totally done in the hardware, right? So it's not an intelligent thing to do. Just take packet, have some hardware, you can put it in the buffer, and that buffer will be again fetched and given it to another interface. So this is easy. Second thing is it has to find out how to forward packets. So that means which interface to use. Now this is a challenging question. We still don't know how to do this. So we'll find out algorithms so that automatically routers can figure out. We don't need to manually tell. So for this algorithm, these are the constraints. So any solution I come up with, any program that I come up with should have these properties. One, the packet should reach the destination. That's the trivial thing, because if you don't have this, that means you just send packet to anywhere and that solves the problem, right? So you have to mention that it should reach the destination. Okay. On top of that, these are the optimizations. You see all minimize, minimize, minimize. So these are all optimizations. This is correctness. And these are optimizations. Typically, every algorithm that you will be asked to design in future will have two criteria. One is the correctness and one is the optimization. So the correctness is easy. Optimization is you can minimize the number of hops. So if you assume every link is just 1 unit of cost, then you just minimize the number of hops. Or you can minimize the delay. That means when you send a packet, it should reach as soon as possible to the destination. Or you can minimize the packet loss. That means you don't care about how many hops it is going, how much time it takes. There should not be a packet loss. Right? So if any link is notorious to drop packets, then you don't use that. Right? So you can do this, or you minimize the cost. So this is totally monetary, a financial thing. If every link has got a cost associated with it, then you just want to minimize your balance. So these are the things. Now, So you can have three classes of algorithms. One is depending upon where the decision is or where you are executing this algorithm. Right? So you can do the source routing. That means the source node knows the entire route and you send the packet using that route. Right? So this will typically happen in which algorithm? Link state. So link state, because it knows the whole topology, it can figure out the whole route at the source itself. So this is typically a link state. This is supported in IP standard. So it's in IEEE standard or IETF standard. It is specified and we can use it. Another one is the hop by hop routing. So that means you don't know the entire route, you just know the next hop. So this will be the distance vector, the other algorithm. And this is a standard routing scheme that IP uses. Third thing which we will not see in this chapter is about virtual circuit. So this is like a telephone network. In internet, everything is packet by packet or data graph, right? So no matter how big data is, you divide it into each packet and every packet can go with a different route. In virtual circuit, you actually establish end-to-end circuit just like a telephone call, right? And every packet will go one after another on that same way. This is not exactly internet routing, so that's why the word virtual, because you don't have a real circuit end-to-end. It's a virtual circuit. So before saying this is the output of the routing algorithm. So whenever you execute an routing algorithm, the output is a table. That table contains, depending upon which algorithm you are using, basically the route to the destination. Right? So in source routing, it's the entire route. In hop by hop routing, it's the next hop. And in virtual circuit, it just which is the virtual circuit number. That's it. So depending upon which routing you are using, you will have three different types of routing tables. And so we'll first, I think, revise these two algorithms, and then we'll see how we will modify this and get back. So let's say our minimization or optimization criteria is the first one, which says we just want to minimize the hop count. It should have minimum number of hop count from source to destination, and every link is one link of cost. So this is the base case for the algorithm, and we just now want to minimize the total distance, and total distance is the sum of individual distances. So our functions are very simple. It's first of all, every link is one, and then we just add it and minimize the final cost. Okay? The routing table at each node specifies the next hop, so you don't need to know the entire graph. And it specifies the distance to the destination. So this is something. So it knows that the final destination is 10 hops away, and for that my next hop is this one. Neighbors can exchange routing table information to find a route. So they will exchange. So now, can you remind me what are the steps of the routing algorithm? And then we'll take an example and go through the details. But does anybody remember? A specific question is, what exactly do the two nodes exchange between each other?
First we take a node with the minimum distance, and then find all the nodes which find which nodes are connected to it, and find which is the minimum node distance node, and then take that node. We find the pairs, kind of pairs to all these nodes.
Right. So, but even before doing or reaching there, what will be the simplest thing to do? So this is something you are going multi-hop away. Let's assume that you don't even have to go multi-hop. Everybody is connected directly to each other. Then how would this algorithm pan out? So let me give a network example. This is A, this is B, and then this is C. So in the first iteration, what will happen? So think about this, you can write it down and then tell me what will happen. You don't have to dynamically think. you need to tell me what is the message that A will send, B will send, and C will send. So everybody is going to send some message when they start executing the algorithm. What will be the content of the message that everybody is sending?
Like what are their neighbors?
Right. So first thing is, so the routing will go over multi-hop, but the simplest case is, let's say you don't even need multi-hop, right? Everybody is connected to each other. Then you just have to know the next hop, right? And you can say packet. So for example, in this case B, if you look at B never has to really do any routing. If both A and C are directly connected to each other. So what B does is that if I want to send packet to A, it is one hop. Packet to C, it is one hop. And do you know how they will learn about this? So one way to learn about B is everybody is sending something called a beacon message. When I say beacon message, what that means is, just like in the seashore, there is a beacon, right? Everyone is sending, so B will say, I am B, I am B, I am B. So C will learn this, that I am directly connected to somebody called B. And this will happen at every node, right? So B knows that A and C are directly connected to me, and the hop is number one, right? So it's just one hopper. So what will A say now? So I have given you the message that B sends. What will be the message from A? One, and this will be then B and 1, right? So this is our first iteration. So this is like, you can assume this. You will learn more if you take a distributed systems course, but I will just introduce you a few concepts of that course. So it's like soldiers marching now, right? When you see the soldiers marching, everybody is standing in one line, and then they take one step, right? And everybody take one step. Similarly, A, B and C, you can assume that they are standing in a line and they take one step each. And when they take one step each, they send out a message, right? And this is the content of the message. So A will say B is 1, this B, C, okay? Now what will be the second step? This is our first step. So everybody has taken a first step, right? And the algorithm is not yet reached to something called a fixed point or a stable point, because A still doesn't know how to send packet to C. After this, if A wants to send packet to B, it can do it. If C wants to send a packet to B, it can do it, and B can send it to A and C. But both A and C still don't know how to send packet to each other. Okay? So we need one more iteration. So everybody will take one more step. So what will be the next step? Okay, so what will be the vectors? So they will just forward the tables? You can do that, you can just forward the table, but you can do something smarter also. So let's take one concrete example. What will A do now after? So this is A's first step, send this message. Okay? What will be the second step for A? So what is A going to do now after this point? So let's look at the routing table of A. Okay. So this is the routing table, and everybody will have a routing table. We're just looking at A's routing table for simplicity. So how many hops A is away from A? 0. How many hops B is away from A? 1. Now, can we fill this?
Not without being stable.
Right. So B has sent me this message. Okay. So now can we fill this space?
Yes.
Yes. How do?
A to B and then plus from B to C.
So, but there will be just one value here. 2. But so okay. So what is the? How do we get the value of number 2?
By like A knows a number of hops to reach B.
Right. This is 1. Very good.
And then from this information,
Right.
A knows the number of hops from B to C.
This one.
So add both of them, we will get the number. Right? This is why
So this is how now C can fill in this information, that because it knows that B is just one hop away. So whoever B is saying I am X, Y, Z hops away from B, I just have to have 1 to all of that, right? A it will ignore because I know that I myself is A, so I don't need to consider it. For C it is 1, so I will add 1 to this. If there is D here, and I am not, A is not directly connected to D, and there is some value X here, I can just add 1 to X, and if I don't have anything here, I will put it. Okay? But let's now, the final thing now. If I have something here for C, what will I do? So what I'm saying is, I have some value 1.
We would add those values and compare which one is less, and that value would.
And then you will, so if it is less, the new thing is less, then only I will change my value. Otherwise I stay with my old value and old. Okay. And so if I want to go to A, there is one more piece of information that's remaining here, right? Which is the next hop. Next hop is, so this is blank because A is itself. If I want to go to B, the next hop is B. Right? No need to send it to somebody. And here also it will be B because I use B's table or B's vector. And that's why it's called distance vector. Because this is the vector that you exchange with everybody, and then it contains distance and then you use those.
No, but like B may be traveling through A to reach C, and then the A will take that value as the shortest part, but actually B is taking going higher that A to take B.
Okay, what you're saying is the loop. There could be a formation of loop, right? So let's assume for now there are no loops, right? And then there is a case of loops, right? And what will happen is that's where the marching thing comes into picture. If you assume that every soldier is marching one step ahead, then everybody will execute this algorithm, and in that case we will not form loops. The formation of loop happens when one soldier is going ahead, second soldier is very slow, right? And then there will be loops. Because you get some scale information, old information, right? And that will form the loops. And we will see at the end of this chapter, we will see what is the loop and how, and in reality there will be loops. Because not every router will have the same process. So what does it mean to be a soldier? When I say soldier, that means basically it's a processor. And when I say every soldier is taking one state at the same time, that means all the CPUs are
All CPUs are working simultaneously.
simultaneously synchronized. So they have the same clock and they execute at the same speed. Right? So that means everybody is 4 gigahertz and everybody is clock synchronized and they move. That will not happen. One router is fast, one router is slow, their times are different. In that case there will be loops, because if you use the old information and combine it with new information, you will form a loop. Right? So that's why I made a very simple assumption that everybody is synchronized and everybody is moving at the same speed. Right? So in my case there is no case of forming a loop. So this is distance vector. Okay? So the way to remember distance vector anytime after this is just to think about that it's a distance and it's a vector. That's it. Right? And every node will just know the next one. Right? If you remember this, then you can again design the algorithm and use that. So this is example that So you just have A, B, C and then D. And if you look at every node, this is the routing table. These are the destinations B, C and D for A. Next hop is B, B, B and the metric is 1, 2, 3. So now this has reached a stable point or a fixed point. Do you know in mathematical terms what is a fixed point? You've taken some course in mathematics and have heard this term, fixed point.
So it would be that after that no changes are
No changes happen, right? So what this means is, now no matter how many times I execute this protocol, 100 times, million times, the tables will still be the same. So that's a fixed point. So you execute your code, and this will happen in all the optimization cases, minimization and maximization, right? So if you reach a global optima or global minima, then no matter how many times you execute the algorithms, you will not change because you are already optimized. So this is a fixed point. For B it is, I have, so A says B, C, D, everybody will go through B, and it's 1, 2. So this is a fixed point of algorithm. Now I made a change. I put this node, this link here. After this, what's going to happen is, once they start exchanging the information, the routing table will change. Okay? So let's go through this example. So when you connect this link, C and A, when they exchange the beacon messages, beacon is I am C, and this will say I am A. You know now that you are directly connected to each other, right? So after that, can you go through the messages? What are the messages that will be exchanged and how do you change the routing table of every node? This is an example for you, a question. So I have connected one more link here. Again, its cost is 1. And then what are the new messages sent by everybody and how do the routing table change because of that? Just write it down and then tell it to me.
Send the information to A.
Let's take a minute. Then everybody can write. Right, so let's go to his table. So what will C say? This is his table.
Okay. So it will update distance from A to B in 1 here.
Right.
It will be directly connected to it.
Right.
Okay. There will be any change.
There will be. So this is what C did. Now everybody is doing something, right? And what will the message that C would say? It will send out a vector message.
It will send the one which has updated. Only the one which he has updated.
Okay, that's fine. So it will send that A is 1, B is 1, D is, A is 1. So this and this, right? It will just say A is 1. Okay, to everybody. Okay, that's good. Now, what is at A?
Now A, since
So
A
let's
knows
modify.
that he is connected to C because C has already sent the beacon
Right.
message.
Right.
So A will update his table and at the same time B will update his table.
Okay. So D hasn't updated anything, right? D hasn't updated anything. B hasn't updated anything. D hasn't updated anything. Okay.
Now,
So A will say that C is 1 hop from it. Okay. Let's just this. And let's assume this is no change, so it will send everything. This will change everything. Send everything. Okay. So now this is first step. Every soldier, so our soldiers are A, B, C, D. They have moved one step ahead. Okay? And after moving that there, now again it's the second iteration. So in second iteration or still in first iteration, because you have received a message, you have to operate on that message. So what will now D do? Let's start with D. So this is his table. He receives this message from C.
he first update his table.
Right?
And
So for A, it says its metric is 3, and what C is advertising now is 1. So 1 plus 1 is 2. So since 2 is less than 3, it will update.
Now when all the soldiers move to the next step, then we'll inform the party that he has up. He can
Right.
send that.
Now he will send this information in a second.
And then everyone
So
will
what about B? It's remain the same because this is 1 plus 1, 2, and this is 2, so it's fine, and C is. So let's come to A. For A, B is 1 hop, that's fine, C is 1 hop, D is 3 hops, right? And when it receives this message saying D is 1 hop from C, 1 plus 1 is 2, so it will modify. Yes, next hop velocity. So everywhere, whenever you change one click, no, here it will be same. Here it will be different. That's it. So this will be C. For B, there are no changes because
that link does not affect the B.
yes, but mathematically how would you say? So A is still 1 hop, so there is no possibility of changing A, right? This is 2. Because you cannot go less than 1. Only thing is this, D and C is 2. So now when it receives a message from here, right, so this is the destination, so 1 plus 1 is 2, so 2 is the same thing, right, so it will not change, right, so mathematically it will not change, right? And that matches our intuition because this link is different and for B there is no change, right? So the thing to remember this is, we have to understand how every node executes something, extends something, and then how it affects it, right? If you look at the whole network, it's very easy. But if you look at tens of thousands of nodes, then you cannot come up with a routing table for every node, right? And in that case, you just have to understand the algorithm and see the algorithm, how it executes. So as you said, this will happen and everybody will update the routing table. So this is what happens in distance vector. Okay. So now is it clear the algorithm, the distributed algorithm, what is fixed point, when will the fixed point change, what is stabilization and so on, and when does it have to change again? Whenever there is a change in the network, you will do the change. Now that was distance vector. Second class of algorithm is link state. In link state, each node shares its link information so that all the nodes can build the entire map of the whole network. So what will each node send? Will be there.
The distance to its neighbor.
In our case, there is just distance is always 1 to the neighbor.
So it will just send the neighbors.
Neighbor list. Okay. So when A gets the neighbors of B, what will it do?
It will always check whether that neighbor is directly connected to A or not. If it's not, then it will update the table.
Right, but we can do a very simple thing. We don't even need to update routing tables for now. What we'll do is, this is A connected to B, connected to C, the same thing, right? So now when B sends to A that I am connected to A and B, so my neighbors are A and C, sorry. This is B, this is B, right? So again, let's go to the model where everybody is synchronized, there is globally synchronized, and then everybody is moving at the same speed. So again, soldiers marching in the locksteps, right? So B will send to A that I am connected to A and C. So B knows, A knows now that this is the state of the network. Okay? So this is what A thinks now. The network is AB. That's it. What will C think? So C thinks that this is the network, and at this time B knows the whole network. Right? Next step. What is the next step? Can you think of what will be the next step?
B will send A that A and C are connected to A and C.
Right? I'm connected to A and C. When this information comes to A, what happens?
Then he also knows that C is connected to A, but since C is not connected to A, so it will be connected to B.
Right, right. and vice versa here. Okay? So in that state, when the message from B comes and you operate, so A and C operate on this message, they know that this is the network. So everybody now knows this is the network. After it's a fixed point. Again, going back to our terminology of fixed point, this is a fixed point of the algorithm, because after this, no matter how many messages you will exchange, you will not change the picture of the network, right? Because you got the entire picture. So how much time, what is the order of time? So if you all know the big O notations, how much time does it take to know or to reach the fixed point?
Number of nodes.
Yeah, so it will be less than number. So you have to come with a stricter bound, right? So how many iterations did we go through this for this case?
One.
One or two, right? So you have something at the beginning, you exchange the message, you go into one more iteration. So let's say two.
Number of edges.
Edges is also, yeah, so it will be edges, but again you can come with, I think, a stricter bound. So let's say your network is like this. How much time will it take for this node to understand where this node is, right? Maximum.
When people search, we have this.
Yes, you are coming close to that. But did you understand how to see the complexity of an algorithm? So you take a scenario where the network is extended like a line, right? And now, how much time, so the maximum spaced out apart nodes are this node and this node, right? So for this node to understand something about this node, it will be the maximum time. All of them here in between will immediately learn about each other. Even here, they will immediately learn about each other. Right? This is the maximum thing. It will take a lot of iterations for this message to come all the way here. So what did it, so you said edges and somebody said number of nodes, that's right, but so what is this called? This distance, does anyone know? So it's called the diameter of the network. Assuming something like a circular, right? So diameter is the maximum distance that you can go in a circle. So a diameter of the network is the maximum separation between any two nodes in the network. And this link state algorithm will typically, for you to learn what is happening on the other edge of the network, it will take order of diameter of the network. Okay? Because that will take to reach the first point. Okay.
But this example is also straight network only.
Right. So I just gave you a worst case scenario, but in any average case scenario, you will see the diameter is the maximum distance of the network. Okay? So the definition of diameter is the maximum separation in the network, and that is how much time it would take, because you cannot take more than this. Right? So this is a very strict bound. Okay. So every node now knows the whole topology. What is the next step? So let's get it. What is the next step? That's fine. But final output is of a routing algorithm. Our problem is to construct a routing table. We haven't constructed a routing table. Everybody just knows the topology.
Now everybody can construct the table because they know the full network.
So, but still you have to tell the node. It's a very dumb device, right? It's a computer. If you just tell him construct the table, he doesn't know. You have to tell something in very simple steps. It should be a computer algorithm. What will do that computer algorithm?
We first look for B, like how many objects need to go to D equals 1. And then we calculate for C minimum number of objects will be
Right. But still, so what will be the simple? What you have learned is distance vector, right? Distance vector is the algorithm that you know we can write in a very simple state. Once you know the whole topology, you can learn that same code here. So this is building on what you already learned. See, A can run a distance vector algorithm now within itself to find out the routes for everybody. So it can simulate B sending this distance, C sending this distance, and so on internally. Right? And it can construct the whole routing table because we know the distance vector algorithm can be written as very simple. So that's a very simple thing, as in but it's not an optimal thing, right? So you have to run this algorithm for every node and so on. So first thing is you have to wait for all the messages and then you run this algorithm. But there are smarter ways. Once you know the whole topology, you can use different algorithms or a simpler algorithm to get the whole topology. Okay, so let's go through, yeah.
But Instinct has a problem, like Instinct says, okay, if the new node is added, then that distance vector will not have the node, but this will be always suppose we add a node B, then this
So we go through this, even the link, right? So what happens through when you add a node, right? So let's assume for now, you're not adding or deleting anything. Simple scenario. So A, B, C, D, these are the links. So now let's assume after exchanging all the messages, every node has the topology. So the topology for A is AB, BC and CD and it's there for everybody. And that part is easy. You just send. So C will send something, D will send something to C and C will just forward it. So after that this is the state. And then you can run a distance vector algorithm or any other graph algorithm to find out graphs. Now let's take an example of the same thing. You add something. So I add link A to C. So what will happen? In this case it's simple now. What will happen when I add a node, add a link, as you're talking about? When you add a node or a link, what happens?
then everybody has to update.
Everybody has to update the whole topology, right? So when you add this link and you say A is connected directly to C, A and C will immediately know that this is the new link. So they will put it here. Right? So this is our first step or zeroth step. Then A will send this to B and C, and same thing C will send it to A, B and D. Right? So now B will learn this. A is connected to C and D will also learn that A is connected to C. After that, no matter, this is a fixed point. After that, how many times you exchange message doesn't matter. And after this, then you come to this state where everybody knows A is connected to C, A is connected to C, A is connected to C, and then you will execute, let's say, a distance vector algorithm internally at every node and construct a new route. Right? So this is how it happens. So both the algorithms can deal with this scenario of change and deletion of link. In here it just takes more time because that information has to propagate all the way to every node. So does anyone know what is good thing about distance vector and what is a bad thing about link state? If I add a link,
Negative links.
or negative, so we just say in the positive one. Let's just have positive things. All the links are positives. But still there is a big drawback. Can you think of that drawback? So my question is, two algorithms, distance vector and link state, you add a link. Right?
Everyone has to update.
Everybody. And in distance vector, some has to update. So this is a very good point. What happens in link state is, you have to send this information to everybody. And then everybody will recalculate the routing table and find us. Right? So there is so many messages and so many algorithms, so much of algorithm to execute. In distance vector, if you add it, you remember, you just propagate to the next hop and they will change, and whoever has to change will change it. Like if your distance vector doesn't change, you really don't have to send this information after that. That's a bad thing about link state. And that's why in the internet, we don't use link state that much. Because it takes time. Okay? So both the concepts are clear. So if those concepts are clear, now we'll see how we do it in the MANET. So let's take a break of 5 minutes, and then I will see how these algorithms will function in a network where there is no base station, there is no infrastructure, everybody is moving very fast, and what will be the complex thing. What is the shortest path? But that is not the question. The question is how a dumb device like a computer who doesn't have any intelligence can find out the routing table. That's the question. We will do multi-hop routing so that because nodes are not directly connected to each other. So this is an example. This is the source, this is the destination, If they are directly connected, that means they are within wireless connection. So it's all wireless now. Even if I show a link like this, that means it doesn't mean that there is a wire. Right? So all of our nodes are wireless nodes. It's not wired nodes. So this is S, this is D, and if they are in direct range of each other, then you can use layer 2 routing. But if they are not in direct range, then you have to send a message to somebody else, and that somebody else will forward it to D. Okay? So these are all wireless and these are mobile. So mobile adds a complexity because by the time you learn that this is the network, this node will move out, right? And this could come very close. And so that means, how do you handle this case? And everybody think of a solution depending upon what you have already learned. How will you handle a case in mobility? A node goes and comes and so on. So if you think mathematically, you have to map it to the problem that you already know for which there is a solution. So how do you map this or reduce this to an earlier problem? Right. Adding it. So this is similar of saying this link is down, and there is a new link. Right? So there are three changes I am doing in the network. Deleting two links and adding a link. And now I execute my whole algorithm again, and it will take care of. Okay? So this is how we will deal with the mobility part. So by the way, out of curiosity, anybody knows what is the maximum separation between two nodes in the network, in the internet? Or do you know what is the maximum separation between two people in the world now? It's a very famous result. 6 degrees of separation, right? And what that means is, choose any two people in the world on the earth, and you can find out 6 degrees, 6 paths, 6 links in between them, so that every next hop is known to each other, so they know each other. So world is coming very close to each other. Okay? So that's in the world. In the internet, what could be, I'm not asking what could be the maximum separation. After that, TCP/IP will give up. It will say, I cannot find your route. I can't find the destination. 30 hops? So let's guess. Let's do guesses then. Yes, it supports, right? But what is when the TCP/IP gives up, right? So ping is little different. Ping is your tasting. What I'm asking is, when you connect to google.com, sometimes it says I can't find, right? And that means it has tried some number of hops. So what is that number of hops? Any guesses? So it's not 30. This is more than 30 or less than? Less than 30. What is it? 12, 30. So it's 60. Right? So in the internet it is 16. After that it says, okay, I am giving up. So you imagine that when you contact any network, any computer in the network, it's at the most 16 hours. Okay? And typically it is far less than 16. So for example, google.com and all these big servers, you can reach within 4 or 5 hops or 6 hops, right? So you don't really have to go to 16. So the point I am making is, in the internet also, the big network in the world, you don't go all the way to 16. And now what we are doing here is all wireless. Don't know what is my next neighbor and what's hot and everything is changing. Even if you have to do it for 5 or 6 or 4 and 5, if you achieve this, you have achieved something bigger than the internet. So if you write a routing algorithm, deploy it in the mobile ad hoc network, and you find out that your packet typically goes to 5 or 6 number of hops, that means you are doing something far bigger and state of the art. Nobody has done this. Right? There are very few cases in the world who have showed that they can over wireless go to 6 hops. If you hear anybody saying I can go 7 hops, 8 hops, that means he's lying. Okay. Okay, so we'll see like what are the challenges, and there are lots of challenges, and because of that this field is not growing very fast. There is very slow deployments. So every node is potentially a router. So you can't say that this is a router and this is a node, right? So you don't need two symbols now in the network. Everybody is a router, so you can use either of these two. So let's just use this one. So my laptop, my PDA, my phone, if it has a wireless, it has to forward packets. And that means it has to use its own battery to forward somebody else's packet. Now that typically doesn't happen. I cannot let my phone battery get exhausted because somebody wants to connect to a website. So that is one challenge.
Even laptop, like laptop only sends its send and receive its own packet, not like somebody else. Unless have proxy server installed.
Yes.
So it's not working as a router.
Right. So you typically don't allow that. But if you want to do a managed network, this will be the case. Every node will have to do that because we want to simplify our problem. When we see a network topology, we don't want to identify a subset of nodes which can do forwarding and which others cannot do. For simplicity, we'll say everybody will do routing. In wired network, that's not the case, but in wireless, we'll assume that.
This means every node will be running in promiscuous mode.
In promiscuous, no. So they don't have to run in promiscuous mode. So everybody knows what promiscuous mode is.
In which all the nodes in a network comes to your
All the packets are visible to you.
Right. Right. So that is the case. So in this case, what happens is, let me just think whether it's necessary. So that is not necessary because so a router will have two interfaces, right? So in our case, it will be. So it's not promiscuous node because these two interfaces are not different in wireless. In wireless, you hear everything. And all of this thing is addressed to, let's say, 192.168 or 1.x for me, not x, let's say 4. Okay? And when this node wants to send a packet to this, it will send it to 1.4. And 1.4 will again forward it to this node using again 1.4. And the packet will come here. And this will also take a copy of that same packet, actually. But this will discard. So it's not like you are accepting packets of all the other nodes. You will just accept your own packets.
But sir, like in wireless, how mobile does not act as router, like even if we connect to the router using mobile, connect to the mobile does not act as router.
Right. So your phone is not running the router code, but you can download an application. So which implements this algorithm, which I will describe soon. Put it on the phone, it can act as a router. So there is nothing that will stop it from. And just like right now you are not running that routing code. But if you put it, it will run.
Even laptop, if I run proxy server, it will act as a router.
No. Proxy is different from router.
So in that mode, I can even install a laptop to make it work as a router.
So you have to download this MANET code from somewhere. Then only it will act as a router.
But
Otherwise, it's not acting as a router.
But even if I run proxy server on my laptop, you can connect to my laptop and then connect to these controllers.
Right. But so it's very simple case of router. It's not a generalized router. It's acting like a gateway. So what he's saying is it's acting like a gateway. So a phone can then connect to this and then send packet, right? And so it's acting as a, you can say it's acting as a router only for that phone. But it's not a general purpose router. It's a gateway. So a nodes transmit and receive their own packets and also forward packets for somebody else. So it's not promiscuous node. You're not getting packets for everyone. Right? Only the packets. So you will think whether I need to forward this packet or not, and you will forward it, and you will accept and receive your own packets. But if the packet is meant for somebody else, you will not accept.
I want to store it somehow so that I decide, okay, I have to send it to this node, so I have to store it and then
Yes.
forward
So
it.
that anyway happens on all the machines, right? And then in promiscuous mode, what happens is even if the packet is not at all meant to you, you get it actually about the network layer. So you can see as a So the application programmer the whole packet. In this case, you as an application programmer, you will not see the packet. The router, the IP, so this code will fit at the IP layer, the oversized third layer, and it will do all this, and you will get a packet which is not meant for you. So that's why it's not promiscuous. So topologies are dynamic in MANET, so it's all changing continuously because the nodes are mobile, but are relatively static in traditional. So in traditional sense, it's almost static. It should consider both layer 3 and layer 2 information because again, finally you have to use the MAC address to give the frame. But we will typically stick to layer 3 because we want to separate out the things. We will not use something in layer 2. Only thing we use link layer or the second layer is to find out connectivity and interference, the signal strength, like the one that you see in your phone, the signal strength. So if you know that signal strength is very good, for example, between A and B, if the signal strength is very good, I put a link there. But if the signal strength is below some point, I take out this link. Right? So this is how I use layer 2. In internet, that is not the case. When you connect two wires on a computer, you always get a link. You cannot say that, okay, I have connected wire, but there is no link. But in wireless, you have to continuously update whether there is a link, there is no link. There is link, there is no link. So that needs to be done continuously. So let's do this and then stop. Another thing is in this kind of network, in graph, now you can say it's a graph. You have a lot of redundant links. That means A is connected to B like this and A is also connected directly. Right? So this is a redundant link. So there are a lot of times what will happen is you get multiple paths. In the internet there is not multiple paths. If you get connected from here to your network through Airtel, there is just one link because Airtel will not do 2 or 3 optical fibers. It's very expensive. Right? So there will be just one optical fiber. In wireless, you will see these multiple links. So that's why now the routing becomes far more challenging. A router typically has a single interface, the one that I was talking about. So it's not a different subnetwork. It is still one subnetwork. In the wired internet, there were 2 different subnetworks. Here it is the same subnetwork. It's just that A can now talk to B and C can talk to B. Right? But A and C cannot directly talk to each other. It's also called as hidden terminal. So C is hidden from A.
Sir, if there are direct link between A and C also, then they can talk.
Then they can talk.
Like you see in the exam.
Yes. So both the cases are there. When they can directly talk and also talk through this, and they cannot directly talk to each other like this, and they have to go through this. But the interface is still same. It's not like B has 2 wireless cards. B still has got 1 wireless card.
No, but like if they are directly connected to each other, why will they talk to B? They can always directly.
Right. So the routing algorithm has to then come with the routing table properly finally. That says A's and C's directly talk to each other. So we'll go through all of these slowly. But the point of this is, it's not 2 wireless cards. It's just 1 wireless card. In router, you have multiple wired interfaces cards. And channel properties like capacity, error rates and everything, these are static in the network, but in this case it's very low. So for example, if there are too many people here, your wireless quality will decrease, not because there are too many laptops, but the human body absorbs the signal, Wi-Fi signal a lot. Whenever there is a water, it will absorb Wi-Fi, 2.4 gigahertz. And because of that, your signal quality will decrease. Right? If we are the only person here, if there are 100 laptops, your signal quality will be better because they are not human. So it continuously changes.
In router, as in router, they have only one antenna, but multiple cards with only one antenna.
Typically the antennas are different. If you have multiple cards, so if you see the cards, wireless card in the old days, PC and CI card, right? If that's what you're talking about, then it has antenna itself.
No, but router only has one antenna and like even 3, 4 comes.
Oh, so the router that you're talking about is, it has not 2, 3 antennas, right? So the home router.
Home router only has one.
and it has got multiple interfaces.
But multiple computers can connect to the router at the same time.
That's right. So okay. So let me say what this here is happening. So if you see a router, you will see multiple LAN cards. If you see the router, real router, you will see multiple LAN cards. Okay. In this wireless router, what I am saying is there is just one wireless interface. Multiple computers can connect to it because it's all wireless, right? It's all broadcast media. So it's just like two of us are talking right now, right? A third person can also talk to you because it's all wireless, and it's just one card. So is this part clear? What I'm saying is on the wireless part there is just one card, but with different connectivity. So let's stop here today, and then next time we'll see other challenges.